So this is exactly what we did with TBGT10 glycan samples. I did the extraction and generated the glycopeptides of TBGT10 and the wild type cell lines, and then did the monosaccharide composition analysis. And we could see that what sort of sugar were there in both samples, if there were any differences. But the only difference was in terms of quantity, not in the quality. So after that, we did the glycosidic linkage analysis on these samples. So the top one is the wild type sample and the bottom one is TBGT10 knockout sample. Now, first thing, what do we expect in these samples when we do the PMS analysis? So we know that we have in the total N glycans, we have oligomannose, we have polymanose, we have complex N glycans. And oligomannose, polymanose will only give you different mannose, substituted mannose like 2 mannose, 3 mannose, terminal mannose, and 3,6 mannose. And the complex N glycan will give you 3,6 mannose and 6 substituted galactose, 4 substituted glucanac, and from the linear we will get some 3 substituted galactose and the 3 and 6 substituted disubstituted galactose from the branching point. And that's exactly what we see in the wild type. We see all the terminal mannose, 2 mannose, 3 mannose, 3,6 mannose coming from the oligomannose and polymannose structures, and the rest galactose and glucanac residues coming from the complex N glycans. Now, we could see here that in compared to the wild type in the TBGT10 double knockout, we had less of 6 substituted galactose, 3 6 substituted galactose, and 4 substituted glucanac. Now, 6 substituted galactose and 4 substituted glucanac means polylactic repeats because it's beta 1,4 glucanac, beta 1,6 galactose repeats. So this less of 6 gal and 4 glucanac means less of polylactic structure. So TBGT10 loss means less of polylactic repeats, and that is what we had confirmed earlier with the Western blot. And less of 3,6 gal in the knockout sample again suggests that there is no branching happening in the TBGT10 knockout cells. Or I won't say no, but the branching is highly reduced in the knockout cells. Means the branching point where you have one arm at the 3 position, one arm at the 6 position, and then these branches can be further, these arms can be further branched into 2, and then that's how you get a lot of polylactic repeats in the complex N glycans. But because of the TBGT10, there is no branching happening, means that we already know that number 16 is a TBGT8, which is previously characterized glucanac transferase. So the next possible enzyme which is working for this branching is the TBGT10, causing this number 17 linkage here. And in the knockout, this linkage is missing, or this enzyme is missing, so there is no branching happening. So there's less of 3,6 substituted galactose in the knockout, and then there is no branching happening in the TBGT10 knockout cell lines. And thus, TBGT10 is basically transferring this glucanac on the 6th arm of the complex N glycan. And because the 6th and the branching is not happening, now we see, interestingly, more of 3 substituted galactose in the TBGT10 knockout cell lines, which basically tells us that there is more branching, linear arm is getting extended on the glycan, and basically it might be a compensation which is done by another enzyme which is similar, like TBGT10, and it's the most possible candidate is the number 16 here, which is a TBGT8, which already characterized enzyme. So this enzyme is compensating for the loss of this enzyme. So TBGT8 not only catalyzing its glucanac transferase activity on the 3 arm, but also at the 6 arm, basically trying to compensate for the loss of TBGT10. And that's how these linear arms are getting extended, and that's how we are getting more of 3 substituted galactose in the TBGT10 knockout cell line. So based on this analysis, we concluded that TBGT10 is a UDP glucanac transferase, and it contributes to the majority of beta 1,6 linked polylactic repeats in the glycosidic linkages in the complex and glycans, and the increase in the three substituted galactose residues in the TVGT10 knockout sample suggests that the removal of TVGT10 is compensated by the increase of beta 1,3 glucanac activity, most likely by TVGT8 enzyme. And we have recently published the study along with other molecular biology and evolutionary analysis. Now I will quickly move to analyzing GPI glycans through electrospray mass spec and discuss the methodology that we use. So we know that GPI glycans are attached with lipid and protein. And in order to analyze the glycan, we need to separate the glycan from protein and lipid part. And we do this using aqueous HF dephosphorylation. So aqueous HF cleaves off the lipid and the protein, and it separates the glycans entirely, and we get it in the aqueous phase. And once we have the glycans separated from lipid and protein, we permethylate the glycan and then analyze them using electrospray mass spec. Now the amino group at the C2 position of glucosamine gives us a great advantage to selectively pick up the GPI glycans in electrospray mass spec. When we permethylate the GPI glycans, the amino group gets converted into positively charged quaternary ammonium ion. And when we infuse these permethylated GPI glycans, um, the GPI glycans appear in the MS1 spectra as triply charged precursor ions. And then when we further fragment them in the CID, which causes further rearrangement of the ammonium ion, it gives us doubly charged species in the MS2 spectrum. And then we further do MS3 CID fragmentation to get the final fragmentation of the GPI glycans. And then based on that fragmentation pattern, we characterize the glycan structures.